Okay, so here on the second 13, what we basically have is a fraction in the numerator, okay, two parts, right, adding them together, and a fraction in the denominator, okay, one part. Even though there's a subtraction here, there's only one fraction, right? Well, this is the sum of two. So the first thing we're going to do is tackle this top part. Okay, you see that there are two separate fractions, or two separate denominators. There's an x here and a y there. So in order to add these together, we need to make sure that they have the same denominator. So to the right fraction, I'm going to multiply by x over x. And to the left fraction, I'm going to multiply by y over y. And what this does is it allows me to have one denominator, xy. So I can add these two fractions in my numerator and get y plus x or x plus y, if you want to write it alphabetically, right? Because there's just 1y plus 1x in the numerator, and then you have x times y on the bottom. Okay, and then that second fraction that we have is just a fraction. So it's just 2x over x minus y, right? Nothing has changed with that denominator that happens to also be a fraction. Okay, so now what we're going to do is simplify this by, rather than dividing fractions, multiplying by the reciprocal. So we're going to have the numerator, which is x plus y over xy, times, and now we reciprocate this, so we get x minus y over 2x.
Wait, we're trying to figure out x and y.
We're just trying to simplify this expression, right? There's no equal sign in our problem, so we're not trying to figure out what x and y equal. We're just trying to see if we can make this fraction plus fraction divided by fraction a simpler looking function. Okay, so we're just trying to simplify. So we have, now we have a fraction times a fraction, right? This thing times that thing. So we multiply top times top and bottom times bottom. Okay, so x plus y times x minus y is one of those special multiplication things. X plus y times x minus y becomes x squared minus y squared. Okay, a special multiplication. The x, y in the middle cancel out. And on the bottom, we have some like terms. X times x gives us an x squared. So that would be a simplified version, x squared minus y squared over 2x squared y, which is just one fraction rather than the two fractions that we began with. Okay, this is number 20. We have an exponential equation, right? Because our variable is in the exponent, which is what makes an exponential equation. We want to know when e to the 3x minus 2 equals 3. And it says, give exact terms in terms of natural log. ln stands for natural log. So it's kind of giving you a hint as to what you should be doing to solve this. So let's do it really easy. Let's do our elementary stuff first, which would be adding 2 to both sides.
Nice.
Okay? We always try to do addition and subtraction before multiplication, before all those other upper division type of equations. So e to the 3x equals 5. Okay, so now we have a true exponential equation. Okay, and you want to get rid of the exponent by taking the log of both sides. Okay, that's how you solve an exponential, is by taking the log. And in this case, it says to take the natural log. Okay, and why might we want to take the natural log for this equation? Because natural log is base e. And since this is base e, we need to have something else that is also base e, so they cancel each other out. Okay, whenever we're solving an exponential, you take the log, and in this case, the natural log. So whatever we do to the left, we log to the left, we also have to take the log of the right side. Natural log. Okay, so now that that is canceled out, we basically have 3x equals the natural log of 5, which is some decimal number, right? Logs change numbers into decimals. So our last simple elementary step would be to divide by 3. Okay, so we would have the natural log of 5 divided by 3 is the exact answer in terms of natural log. Okay, because part of the calculus test is going to be non-calculator. And you're not going to have a calculator to figure out what that decimal is. Okay, number 12 wants us to factor. Okay, hopefully you're able to recognize this is a special cubic factorization. Okay, a cubic factorization. Okay, and there's a formula for that. And of course your internet can tell you exactly what that formula is, because Lord knows I haven't memorized it. Okay, but as you do these more and more often, hopefully you will be able to recognize when to use this. So if I had a cubed minus b cubed, right, in general, a cubed minus b cubed. So 8 is in fact a perfect cube, right? It's 2 raised to the 3rd power. It's 2 times 2 times 2. So this is a perfect cube. So this factors to this type of a form. A minus b, right, as a linear type factor, multiplied by a squared plus 2ab's plus b squared. Okay, and this is the formula that Siri would tell you if you asked her what this factorization for a difference of cubes would be. Or else she'd say, I don't know what you're talking about. She'd say, please talk to me in English, if that's what you talk to her. Okay, so here the a value is x, right, because it's x to the 3rd power, and the b is the number 2 because 8 is 2 cubed. Okay, so this is a special factorization. Now, if this were a plus in the middle, I believe both of these would be, one of them would be a plus and one would be a minus, I think. But once again, there's a formula that I have not memorized. So if you need it, look it up. So we have x minus 2 as our linear factorization. And then we have x squared plus. So this is 2 times x times 2, which is 4x, plus 2 squared, which is 4.
Oh, so you got the 2 from cube root of 8, right?
I got the 2 from taking the cube root of 8. Yes. Okay, so if you can recognize it as a special cubic form, then you can use the special cubic formula in order to factor it. Okay, special cubic formula. Okay, on 14, once again you want to simplify, right? There's no equal signs, so there's no solving, right? We don't care about what the value of x is because we don't even know what it equals. We just want to simplify this expression. So we have a fraction plus a fraction, right? And in order to add fractions, we have to have the same denominator. So on the right side, we'll multiply by x plus 3 over x plus 3, right? So this one multiplies to that side, and that one multiplies to
X plus 2 over x plus 2.
this side, x plus 2 over x plus 2. Okay, and you do it to the top and the bottom because mathematically speaking, we're multiplying by 1, right? This, anything divided by itself is 1. And you're allowed to multiply by 1 because that doesn't mathematically change your number or your equation. Okay, which is why this is mathematically legal. So we have some things. We have to multiply x plus 2 times 1, which is just x plus 2. Yes?
Yep.
And then plus, we have to distribute the 5 into these things on the right side.
5 plus 15.
5x plus 15. And in your denominator, we have the product of 2 binomials. If you want to multiply it out, be my guest. If you don't, that's perfectly okay also.
Oh, you don't have to.
You don't have to.
Oh.
Okay? The main thing is if this were a multiple choice question, you need to make sure that the answer that you get matches up with one of the 5 choices, right? And maybe you didn't simplify this bottom part, but in the questions they did. So you have to be able to recognize your answer with what is represented as A, B, C, D, or E. Okay, but chances are they would add across the top, right, making 6x plus 17, but they probably wouldn't simplify the bottom. Okay, that might be how they represent the answer. Or they could have it multiplied out x squared plus 5x plus 6. Both of those might be an option. Okay, but you need to know how they got their answer from where you have your answer. Okay, 16. Okay, we want a formula for, once again, the composition, right? This means composition. So we're going to take the g equation and plug it into the f function. Okay, we're going to take root x minus 3 and plug it in right there. Okay, so that's what a composition does. It replaces a letter with an equation. Okay, but this one also says something about the domain. Right, and domain are all your possible values of x. But better, they are the restrictive values. What ones can you not use in this function? Right, like our food allergies. It's my favorite way to describe a restriction is your food allergy. If I'm allergic to bees, right, to the sting of a bee, and I get stung by a bee, chances are I could die. Right? I'm allergic to bee stings. I personally am not. I don't carry an EpiPen. But if you do, stab yourself in the leg with an EpiPen. If you get stung by a bee, I will stab you in the leg with an EpiPen. I will do that for you. I will save your life. You're welcome. So the domains. Let's talk about the domains. The one on top, this one here, that is a rational function. The domain restriction is your denominator can't be 0. Okay, so in other words, we can't have 0 in that denominator. Everything else is good because you're squaring it. It'll be all positive, but you can't have 0. Okay? Because it can't be 1 over 0. We can never have a 0 in the denominator because it's undefined. Yeah, vertical asymptotes, holes, removable dots, discontinuities, all those wonderful things. Okay, can't have a 0 in f because it's a rational function. For g, this is a square root function. And we have to make sure that you don't take a square root of a negative. You can only take square roots of positive, okay, non-negative, 0 and everything else. So we have to make sure that we're not plugging in any numbers that would make that negative. So we have to use only numbers greater than or equal to 3.
Because
Okay?
3 minus 3 is 0. So
Because 3 minus 3 is 0, and anything less than that would give us a negative square root, and we can't take negative square roots.
Can you give a square root of 0?
Yes, it's 0. Yes, that's good.
I didn't know that.
Yeah, that's fine.
I thought you could
Right?
have a 0 in a radical.
But the square root of negatives are imaginary, right? Those are our complex numbers when we're taking the square roots of negatives. Okay, so this is me. I have only numbers larger than or equal to 3, and now I am going into the bottom here. Okay, so 1 over square root of x minus 3 squared. So here's the composition parts. We are replacing x with root 3 minus x. Okay, and when I square a radical, those both go away. So I am left with the rational function 1 over x minus 3.
Oh, okay, you just plug the g of x to the f.
Yes, I plug the g into the f. Okay, now talking about domain, my domain is going to change a little bit, right? Because here it could be equal to 3, but what if I plug 3 into my denominator now?
It'd be 0.
It'd be 0. So I can't actually have my 3 anymore. Now I am strictly greater than 3 is the domain for my composition. Because in a denominator, I cannot be equal to 0 anymore. Right? Radicals are fine to be 0. Denominators are not. So I have to take away the or equal to part and strictly be greater than. Okay, and these are some of the hardest ones to figure out as far as the domain goes, because the domain changes when you do compositions.